I'm hopeful that examples 2 and 3 from the previous video were a little bit of review for you and that you did not completely forget how to do a Lewis structure. What I'm going to show you with 4, 5, and 6 are some kind of weirder examples that you're going to see. And these are things that we intentionally left out of regular chemistry because they were honestly a little bit more complicated than you needed to deal with. But it's AP now, so, bring it on, I guess. So we're going to start off with, for number 4, PF5. Now, this is one of those situations where I told you that sometimes with your nonmetal and nonmetal pairings, oxidation numbers get a little bit weird. So I just want to go over with you what is happening in this situation. Normally, when we look at our oxidation numbers, we say that phosphorus has a -3 and fluorine has a -1. So hopefully that's something that is familiar to you. However, when we have nonmetals and nonmetals getting together, one of the elements has to have a positive oxidation number. And typically, not always, but typically, the element that's written first is the element that's going to have the positive oxidation number. And in the case of this particular compound, the fluorine always is a -1, so that helps out too. So in this situation, we have fluorine being a -1 for its oxidation number, and there are 5 of them, so the total charge for fluorine is a -5. And there's 1 phosphorus to cancel it out, so phosphorus's oxidation number has to be a +5. And so if you were able to come into my room, you could take a look at the periodic table and realize that there are lots of different possible oxidation numbers for your nonmetals. Like nitrogen, I think, has, I want to say, like 5 or 6 different possible oxidation numbers that you can run into because of the non-metal to non-metal compounds that it makes. So what happens then is when we have these kind of weird oxidation numbers happening, we also have other weird things that can happen as well. And so in this case, you see this little subscript of 5 and you say to yourself, I've never seen anything that has 1 element here and 5 down for the subscript. And that's because once you get into the 3rd period on your periodic table, so starting in the 3rd row, you have elements that have a D shell that's available to put electrons in. And so if I have a D shell that's able to have electrons put into it, I can start to kind of jam things into that D shell that maybe we wouldn't be able to do with elements that are higher up on the periodic table. And one of the consequences of that is that I can make more than 4 bonds with any element in period 3 or lower. And so we're going to start this process off, but the center is going to look a little bit different for this element. So just like before, I need to figure out my valence electrons. And just because phosphorus has an oxidation number of 5 doesn't mean it changes its number of valence electrons. It still has 5 electrons. Fluorine still brings 7 electrons to the table, and there are 5 of them now, which is a lot. This leaves us with a total of 40 electrons. So we have a ton of electrons that need to go into this Lewis structure. P is still going to be in the middle, but instead of only being able to draw 4 lines, because phosphorus is in that 3rd period, I am now going to draw 5. And you can draw up to 6 lines depending on the particular element. Sulfur and selenium sometimes will end up making 6 bonds, so just be aware of that. And sometimes in these situations, even your noble gases can make bonds, which is just poof, mind blown. All right, so we are in this situation. We've got kind of, it looks like a star almost, and I drew in 5 lines. So I'm going to take away 10 electrons from my count, and that leaves me with 30 electrons on my picture that I still have to add. So I'm going to take care of my fluorines, and I'm just going to draw in the lines here, remembering that the lines represent 2 electrons. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. Now you say to yourself, okay, each of these fluorines is satisfied, 2, 4, 6, 8 for its octet. But phosphorus here has 10. And that is okay. What we call this is an expanded octet. So you can have up to 10 electrons in the case of phosphorus, and that is totally fine. So just be aware that that is a completely legal Lewis structure, and it's something that you see if an element has a place in the third period or lower, because it has availability for that D shell. Okay? All right. The next one is going to be ICl4 minus 1. Okay? So we look at this. Doesn't look like anything super crazy because it's got 4 for a subscript for the chlorine, so that's not so bad. So let's get started. Iodine brings 7 electrons to the party. Chlorine also brings 7 electrons to the party. And there are 4 of them, plus the 1 straggler from the -1 charge. Remember that if you have a positive charge, that positive charge takes away 1 electron from my total here. And so if I look, I have 28 right here, plus 7 and another 1. So 28 plus 8 is 36 electrons. And I'm going to draw. I goes in the middle. I'm going to put my CLs distributed around here. And then I'm going to start to do my math. I've drew 4 lines in here, which means I've got to take away 8 electrons. When I take away 8 electrons, that leaves me with 28 electrons left. That's terrible. You can't see that. 28 electrons left to draw in my picture. So I'm going to start with my outside. 1, 2, 3, 4, 5, 6. I regret my choice not to do lines. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. So you say to yourself, well, all of my CLs have a full octet, and my iodine also has a full octet. So what the heck is going on here? This is another type of expanded octet that we see. So iodine exists in a period that's lower than the third, or the third period or lower. So it can have an expanded octet. And so what ends up happening is if you have extra electrons, and in this case, I have 4 left over that don't have a place to go, what happens is they will hang out by my central atom. And that's because those extra electrons can go into that unoccupied D shell and then hold space there. I kind of think about the central atom like, you know, that drawer that you have in your house somewhere where like all the random crap goes. I call it your junk drawer. I think of the central atom as putting those electrons in the junk drawer. The extra stuff, the central atom is going to take care of that. So again, you're going to see those extra things showing up on your central atom. And you have, in this case, 2, 4, 6, 8, 10, 12 electrons on your central atom. And that's totally okay in the case of iodine. Now, remember that this is an ion, so we have to put a -1 and a set of brackets around it as well. Okay? All right. And our last one is going to be NO. No, I don't want to do that. No, it's nitrogen monoxide. So in this case, we're going to draw our Lewis structure. You say to yourself, what seems weird about this? 5 electrons and 6 electrons gives me a total of 11 electrons. And you say to yourself, you told me that I need to have an even number of electrons. Every once in a while, you will find a compound where I have an odd number of electrons. When you have an odd number of electrons, your electron configuration, not your electron configuration, I keep screwing that up, your Lewis structure is going to be a little bit different. So we're going to kind of just go with what we've done so far. So I'm going to have N connected to O. When I do that, I'm going to have 2 electrons taken off, and I'll have 9 electrons left. I'm going to start adding things to my outside to keep my octet satisfied, and we'll kind of see how things go. So I'll start on the O. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you look at that, you're going to say to yourself, this is an impossible Lewis structure. How in the world am I ever going to draw this thing? Well, we could, since the N is short, in this case, 3 electrons, I need 3 more. I can get 2 electrons by making this a double bond. So let's try that. Okay, so if I look at this, O has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 7. So I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in the picture. And there's no way that I can really make this work. And honestly, it's okay. When you have compounds that have odd numbers of electrons, and again, it is rare, but I want you to know what happens. You have this kind of odd hanging electron on the end there, and that makes this compound called something called a free radical. Now, a free radical is an element, or not an element, I'm sorry, it is a compound that has one kind of unpaired electron. These compounds are very reactive. So what happens is this electron seeks out a mate or a pair to get together with so that it can react with something and stabilize itself. And so these free radicals are incredibly reactive, and they don't stay this way very long. So they seek out something to bond with to pair off that electron and deal with the unstable nature of it. So just so you're aware, you do see this once in a blue moon, and if you see that kind of single electron hanging out there, that's what that is. All right. On your homework, you're going to be asked to try some of these Lewis structures. Give them a try, and if you find yourself having questions, make sure you come and ask, and we'll get things cleared up. All right, good luck.